This is the fifth in a series of videos in which I'm showing various ways in which a Fluke 9010a troubleshooter can be used to fault find on various bits of electronic equipment. In the previous videos I went through how to hook up the pod. There's a different pod for each processor type, and then the various ways of creating programs and the basic fault finding that you can do with the built-in Fluke functions. In this video I want to look at the probe. There is an additional attachment to these units, which is the logic probe. Now, unlike most logic probes, it's got some quite nice features that when properly used can really make fault finding on complex devices a lot easier. I think the probes are often underused because it may be underestimated just how powerful they can be used as a fault finding tool. So I'll only be going through the basics in this video, but hopefully it will give you enough so that you can realize, if you don't already use the probes, just how useful they can be. So the probe is a fairly simple assembly, but of course it doesn't work standalone. It doesn't need to be coupled to the 9010a. You can't use it as a standalone logic probe. As ever, by the way, I do supply the bare boards on my website, so you can attach the cables and a probe and use it without a case. But I generally make simple 3D printed cases that I put mine into. It just protects the probe from accidentally shorting onto the board that's being tested. But you don't need to do that if you don't want to. You can just use them as a bare board assembly. But once assembled, they are quite a nice compact unit. Now, what I tend to do is fit lenses to the LED positions, just to make it easier to see. Otherwise, surface mount LEDs do tend to be they're quite bright, but you need to be looking directly down on top of them. By fitting lenses like this, you can see them at more or less any angle. If I set the Fluke to pulse high, you can see quite clearly that you don't need to be looking directly at the LED to be able to see it when you've got a lens fitted. It's also, of course, quite bright. It does tend to focus the LED light directly upwards. And same with low pulsing, you can see that very clearly as well. Okay, so basically what the probe does is it can respond to circuit stimulus, so it can pick up transitions of signals on the unit under test, but it can also be used to inject signals into the unit under test. It can do those both at the same time if you want it to. It can also capture data from the unit under test, and it can also generate signatures, or what are called signatures, from the unit under test. That's very useful if you do have a working example of the unit you're trying to repair. So we'll just go through these basic functions in this video. If at the end I've missed something that you want me to cover, then leave a comment and I'll do a follow-up video. But the manual's quite good. It does go over these in quite good detail. So what I've got set up is the Z80 pod, a very simple breadboard. The breadboard just consists of a clock generator, because obviously the module does need a clock fed into it, and in this case, just to simulate a simple unit under test, I've got a counter divider chip. I was going to use one of the units I'm repairing to demonstrate the probe, but I thought it would just be easier using a very simple setup like this. So in general, the probe specification is quite straightforward. The default state is for the output to be floating. You can set it to pulse high or pulse low, so I'll attach the scope probe, and you can see that on the scope we are currently floating, so this is essentially tri-stated. We can then pulse high, so if I turn on pulse high, you can see we're now getting a series of high pulses coming out of the probe tip, and the red LED is flashing. And we can pulse low, so if let's move the trigger point, so you can now see that we're getting a series of low pulses, and of course you can do those both at the same time, so we'll go from rail to rail essentially and give you a full amplitude pulse. That gives you total control over what you're actually feeding into the circuit if you're trying to give it a stimulus. So it might be that you're trying to stimulate a particular node on the board, and you might want to go from tri-state to low pulses, or tri-state to high pulses, or both, and that is obviously what you can do. But the probe can do far more than that. So we'll look at the probing functions first, and what I've got on the board, as I say, it's simple setup with a clock generator chip. It's running at about 1.2 megahertz, but looking at the circuit with the scope, you can see this is our clock. So you can see it's about 1.2 megahertz or thereabouts. That's been fed into this divider chip, and then you can see that we're getting a binary sequence coming out of this. It's not doing anything in particular, this is just here so we can give the probe something to trigger on. If I take the probe, if we try looking at these same points, if you want to test the clock, hopefully this will be visible on the camera. So we're now getting the red and the green pulsing, and that means that we are getting a signal that's going below the low threshold and above the high threshold. By default, the setup on these probes is that the high threshold is around 2.4 volts, so anything above that will turn the red LED on, and the low threshold is about 0.8 volts, so anything below that will turn the green LED on. The pulses, or the indications, are stretched to a minimum of about 250 milliseconds. So if you got fast pulses such as the ones we have on the clock on this board, then it will stretch them so they are visible, and you'll get a quarter-second flash of the LED, and then it will re-trigger on the next edge after it turns off. So if you're getting a stream of pulses, then the LEDs will flash. It won't give you that much information about the frequency, so if I put it on these, although we know that these are all different frequencies, the LEDs are flashing at the same rate. It's just telling you there's an active signal on there, but it won't give you any information about what the frequency is. That's not really what the probe is for. If the signal was just going low from a tri-state, then only the green LED would flash. If it was going high from tri-state, then only the red would flash. So it does give you some fairly good information as to what the signal is doing, even though you're not looking at it with a scope, it's just the probe. Most logic probes will do that, so there's nothing special there, but that's just the basic mode that you can use this in. So when we move on to the more advanced features of the probe, it will become more apparent how useful it can be in fault finding. The first thing to bear in mind is if we want to capture some data using the probe, then obviously what we can do is just attach the probe to the node we're interested in. And you can see here that we're just looking at one of the outputs of the divider chip on the unit we're testing. And we're getting full amplitude signals here, so both LEDs are flashing. And if I press the read probe key on the Fluke, then it will read the data stream coming in through the probe. So you can see that the event count is 96. That will update each time I press the key. There is no signature that we're capturing here, we're just doing a raw capture of the data. And all that's happening here is it's capturing the data stream coming in through this particular node. It's not particularly useful in this mode, but it can tell you if there's something going on, and you can see what the data stream is by looking at this later. When you capture data in this way using the read probe key, then the data that you're capturing is actually stored in the internal register 0. So if you look back at the videos I did on programming, you could you could write a program that looked at these values and interpreted them in whatever way you want. So the data is stored when it's captured, and you can either explicitly look at the register in a manual mode, or you can include a read probe command and then interrogate the data within a program. In free run mode like this, so you can see the probe is just continually capturing data. It's not particularly useful for doing in-depth fault finding on a board. In general, what you're trying to do when you fault find is pick out the data you're interested in from the activity, the background activity that's going on within the machine you're testing. And that's what can be quite difficult to do, and where a logic analyzer can come in very handy. You can, however, do something similar to that, albeit much simplified, using this logic probe. At the moment, the capture is in free run, so it's just continually running. But what you can do is set the sync mode of the Fluke to capture on certain strobe signals, in this case on the Z80 bus. They're called sync signals rather than the specific memory address signals that the Z80 uses, simply because there are many different processor types that the Fluke supports, and rather than having to try and remember what each particular processor refers to certain control lines under, then the Fluke just refers to them as sync. So the basic ones that you have for all parts are the address sync and the data sync, and they are, if you like, event periods that are specific to a data bus access and address bus access. So in other words, if you want to look at an event on the address bus at a certain address, then what you can do is you can hit the sync key and then put it into A mode, which is address. And what will happen now, you notice that we've stopped flashing on the probe. So if we try and do a read probe, you can see we're capturing, but if you looked at the data, it would all be zero. It's not actually capturing anything. But what we could do, for example, is perform a function that will cause the address bus to be accessed. So if we do this, you can see that during the test the probe was flashing. If I repeat the test, you can see that both LEDs are flashing. So the important thing to bear in mind is that when you set a sync mode, then the probe is only active during the active part of the cycle you're syncing on. So the other one you have is data, so if you press sync D, then that will set up for data, and you can see the LEDs have gone off. If we repeat our ramp test, again you can see that the probe is active only during the test. If I press repeat, you can see that the probe is active again, but only during the period of the test. But notice the signal is continuous, so although the signal is going all the time, we're only capturing data while we are triggering on the specific sync that we've selected. And of course we can set it back to free run when it's going to be running all the time and giving us the normal indications. Now it does exactly the same thing when you do a write. So if you want to cause the probe to give a stimulus to a circuit, then you do the same thing in terms of setting up the sync, but you then do a write function rather than a read function. But also the ramp will do the same thing. So when you do a ramp function, if I clip the scope probe to the end of the logic probe and we repeat the last test that we did, notice that we're in free run, but there's nothing coming out of the scope at the moment. If we go into sync mode and we'll select address, and then we'll do a ramp test, notice there's nothing coming out of the probe because we're actually doing a read. So this is in passive read mode, so there's nothing going on here. However, if we set the probe to provide the stimulus, so turn high on, and then we'll do a read, or rather a repeat of the same test that we just did, you can see that the probe isn't flashing now because we've got this set to a particular sync mode. But if we do a specific test, you'll see that we're getting a signal coming out of the probe. If I turn on the low pulse on the Fluke and we repeat this test, you can see we're now getting high and low, and we're getting both LEDs coming on the probe. So in other words, the activities provided and the functions provided from the Fluke can be controlled to certain parts of a bus cycle, whether that be address bus or data bus, by selecting the correct sync mode. And that means that you're only detecting or injecting signals into the unit under test at a specific part of that bus cycle. And that does mean that if, for example, you want to capture data from a specific address, then you can do that. You would just set the Fluke up to read from a specific address, attach your probe to the node you're interested in, set it to read, do a capture, and then what you would end up with is data in register 0 of the Fluke that came from the node at the correct part of the bus cycle that you're interested in. So I hope that made sense. It sounds a bit confusing, but when you start using it, it's quite straightforward. Now, the other thing to bear in mind with the Fluke when you're reading the probe is it does not differentiate between a stimulus it is generating itself and stimulus on the unit under test. So, for example, if you have the Fluke providing stimulus output, then it will read that as part of its input. That's just one thing to bear in mind. If you do want to read data from the unit under test, then really you need to turn off the stimulus from the probe itself. The last thing I want to cover in this video is how to capture signatures. So a signature in this context is nothing more than a value assigned to a bit stream that's been captured from a particular node on the unit you're trying to test. And the idea is you capture a signature on a particular node on a unit under test that you know works, and then you compare that against the same signature captured from the same node on a faulty unit, and you can then see what the error is, and that should give you an idea as to what the faults are on that particular machine. So what I'll do is to show how to capture a signature. So if we look at the same node we were looking at before on this unit, you can see that both LEDs are flashing, so we're in free run mode here. And to capture a signature, what you have to do is select either address or data sync modes. So I'll do that on the Fluke now. I'll press the sync key and we'll select address. So we're now in address mode. Notice that the LEDs have stopped flashing, so the probe will now only read data during a memory address cycle. And we'll do a test that will create some sort of signal on the address bus. So in this case we'll do a ramp test, and we'll ramp at FFFF, press enter. Notice that the LEDs on the probe flash for the duration of the test, and it takes a second or so. The test is now finished. But what we can now do is read the probe, and notice that we now have a signature shown, and that's the signature that was captured from that node during that particular test. And what in theory you can do is go to a faulty unit, do the same thing, and see if you get the same data. Now of course you would need to make sure the testing you're doing is the same each time, otherwise you're just going to get random data. So in other words, writing to a specific address, writing a certain value to a specific address, you capture that, capture the signal, and then you can compare that against a non-good unit and see if there's a fault on that particular node. And you can do this for multiple nodes. So for example, let's say you're trying to sort out a problem with a serial bus interface. You could capture the data on the right line, for example, by writing a certain hex value to it, capture the signal, and then check a non-good unit and see if you get the same results on that unit. I've only really just scraped the surface here with what you can do with this probe. It is a very powerful tool once you get familiar with how to use it. One other feature of the Fluke that's worth mentioning is the trigger output on the back of the Fluke. Currently I have the external trigger of the scope connected to it, and that sync pulse coming out of the Fluke is synchronized with the operation of the probe. So whenever the probe is triggered to start reading a node, for example in address mode or data mode, then that sync pulse will occur, and that means that you can cause the scope to trigger at the same instant that the probe starts to capture data. And that can be quite a useful tool in just using the probe to capture data on certain parts of a bus cycle, or even at certain addresses or certain data values. within the unit under test. And again, if you have your scope or even your logic analyzer connected to that sync output, then you can capture data synchronized by the node you have the Fluke probe attached to. So all these things combined make the probe a quite a useful addition. If you do have a Fluke, it's well worth getting a probe. Spend some time playing with it. As I say, I've only really scratched the surface here with what these can do, but they are very useful things to have. Again, it's one of those things I don't use that frequently, but when I do need it, it is a very useful tool to have, and it has on occasion saved me a lot of time fault finding. Any questions or comments, or if you want me to cover anything in more detail, then please let me know.